You think time runs forward because that's how the universe works. You imagine time as a river, always flowing, never turning back, a law of nature, obvious, untouchable. But that's not what physics says. Take a coffee cup, a simple cup, sitting on a table. You know what happens next. It falls, it shatters, pieces scatter across the floor. You have never seen the opposite. Shards trembling, sliding, assembling, leaping back into your hand. You call this the direction of time. You call it cause and effect. You call it reality. But physics, at its deepest level, does not forbid the pieces from reassembling. Not really. The laws that govern every particle in that cup barely care about past or future. They run just as well backward. So why does the cup never unbreak? Why does time seem to have a direction at all? And if the answer hides in something as ordinary as a broken cup, what does that quietly say about time travel? You believe the falling coffee cup proves something fundamental. You see the cup slip from the table. You watch it strike the floor. You hear the fracture. Ceramic becomes fragments. To you, this feels like a law of nature. Things break. They do not unbreak. The direction seems built into reality itself. But this is the first mistake. What you call a law is only a pattern you have never seen violated. Look closer at the moment the cup shatters. Nothing mystical happens. No special force appears that commands the cup to become pieces. There is no instruction in the universe that says break, but never reverse. There are only atoms, colliding, vibrating, pushing one another according to simple rules. Every fragment flies outward because its atoms exchange momentum with the floor. Molecules strain, bonds snap, energy spreads through the material like a wave. That is all. Now imagine something unsettling. Film the entire event, the fall, the impact, the scattering shards. Play the recording backward. The fragments tremble, they slide across the floor, they gather, they fuse. The cup rises and lands softly on the table. It looks absurd, unnatural, impossible. But here is the uncomfortable part. The fundamental motions of the atoms themselves do not object to this reverse sequence. The tiny collisions between particles, the pushes and pulls that govern matter, work just as well in reverse. At the microscopic level, the movie played backwards still obeys the same rules. This is not speculation. This is how the known laws of motion behave. The equations describing particles do not insist on a preferred direction from past to future. They simply describe change. As Richard Feynman repeatedly emphasized, if you reverse the motions of every particle in a system, the equations continue to function perfectly. Nothing in the basic machinery of physics demands that a cup must shatter rather than reassemble. And yet you have never seen shattered pieces leap together. So where does your certainty come from? From experience, from habit, from overwhelming consistency. But consistency is not the same as necessity. You confuse what always happens with what must happen. The falling cup feels like proof that time itself pushes events forward, from order into ruin, from whole into broken. It feels like evidence that the universe contains a built-in direction, but at the level where reality is actually governed, no such direction is written. The breaking of the cup does not reveal a fundamental rule about time. It reveals something else entirely, something quieter, something statistical, something that hides behind what looks obvious. And the moment you accept that the cup's destruction is not enforced by law, your picture of cause and effect begins to loosen. Because if the basic rules allow both directions, then the difference between past and future is not where you thought it was. You expect the universe to remember what just happened. You expect the present to depend on the past, never the other way around. Cause first, effect later, always. This feels so obvious that questioning it seems absurd. But the deeper you look into physics, the less this certainty survives. Consider what a physical law actually does. A law of motion does not command events. It does not declare what must happen next. It simply describes how a system changes when particles interact, how positions shift, how velocities evolve, how forces alter motion. And when physicists write these laws down, something strange appears. They almost always work perfectly well forward or backward in time. Take the motion of a planet orbiting a star. If you reverse its velocity and make it retrace its path, the same equations still describe its movement. Nothing in the mathematics objects. The orbit unwinds exactly as it formed. Or think of colliding billiard balls. One ball strikes another. Momentum transfers. Directions change. Now reverse every velocity. The balls separate, collide again, and return to their original positions. The equations remain satisfied at every step. The laws themselves never insist which direction is forward. This symmetry runs deeper than simple motion. The equations governing electricity and magnetism behave the same way. The rules describing atoms and molecules do the same. Even the strange mathematics of quantum mechanics, the framework governing the smallest scales of reality, largely preserves this symmetry between past and future. At the fundamental level, physics describes a universe where time has no preferred direction. This is not how you imagine reality. You imagine a built-in push from past to future, a one-way mechanism embedded in the fabric of existence. But the core laws do not contain such a mechanism. They allow a movie of the universe to run either way, forward, backward. Both are permitted, so something peculiar emerges. Your everyday experience tells you time has a direction. The laws of nature say otherwise. You live inside a contradiction. To see how deep this goes, consider the rules of motion first described by Isaac Newton. These laws predict how objects move under forces. If you replace time with its negative, if you run the clock backward, the equations still hold. The trajectories remain valid. Modern physics has expanded far beyond this framework, yet the pattern persists. At every level where we describe the behavior of matter, time's direction seems optional. You think time runs forward because that's how the universe works. You imagine time as a river, always flowing, never turning back, a law of nature, obvious, untouchable. But that's not what physics says. Take a coffee cup, a simple cup, sitting on a table. You know what happens next. It falls, it shatters, pieces scatter across the floor. You have never seen the opposite. Shards trembling, sliding, assembling, leaping back into your hand. You call this the direction of time. You call it cause and effect. You call it reality. But physics, at its deepest level, does not forbid the pieces from reassembling. Not really. The laws that govern every particle in that cup barely care about past or future. They run just as well backward. So why does the cup never unbreak? Why does time seem to have a direction at all? And if the answer hides in something as ordinary as a broken cup, what does that quietly say about time travel? That word should make you uncomfortable, because if the fundamental rules do not distinguish past from future, then the familiar arrow of time, the sense that events irreversibly unfold, cannot come from those rules themselves. It must emerge from something else, something not written in the equations of motion, something not enforced by fundamental law. The broken cup, then, is no longer evidence of time's direction. It becomes a puzzle. Why does reality consistently choose one direction if the rules allow both? Why does the universe behave asymmetrically when its laws are symmetric? The answer cannot be found in forces or equations alone. To understand it, you must abandon the idea that impossibility is what prevents the cup from reassembling, because the universe does not forbid the reverse. It merely makes it unimaginably unlikely. And that changes everything. You think the cup stays broken because it cannot reassemble. You think the universe forbids it, but the universe does not forbid it. It overwhelms it. There is a difference. To see it, forget the cup for a moment. Imagine a box filled with air. The molecules inside are in constant motion. Countless tiny particles rushing in every direction, colliding, scattering, changing course. Their movement follows the same time-symmetric laws you just encountered. Every collision could, in principle, reverse. Now consider something strange. At this very moment, nothing in the laws of physics prevents all the air molecules in the room from drifting into one corner, leaving the rest of the room empty. No force stops them, no rule forbids it. Yet you never see this happen, not because it is impossible, because it is absurdly unlikely. There are vastly more ways for molecules to be spread out than clustered together. The number of possible arrangements where the air fills the room is unimaginably larger than the number where it gathers in one corner. So the spread out state dominates, not by law, by statistics. This is the first step toward understanding the broken cup. When the cup shatters, its atoms move from a very specific arrangement, a smooth, continuous structure, into an enormous number of possible scattered configurations. There is only a tiny set of ways for those atoms to form a perfect cup. There are countless ways for them to be fragments. The difference is not small. It is astronomical. To reassemble the cup spontaneously Every particle would need to move with extraordinary precision. Every fragment would need to slide into exactly the right position. Every vibration would need to align. Every surrounding air molecule would need to cooperate rather than interfere. Nothing forbids this choreography, but the number of ways it could fail exceeds the number of ways it could succeed beyond comprehension. So the cup remains broken, not because the universe demands destruction, because disorder is statistically favored. This idea replaces certainty with probability. What you experience as a rigid direction of time is, at its foundation, a drift from unlikely states toward overwhelmingly likely ones, order into disorder, structure into possibility. The universe does not push things forward. It merely wanders where possibilities are most numerous. This is a very different picture of reality. It means that the arrow of time, the sense of irreversible change, is not a fundamental command written into nature. It is a statistical tendency emerging from enormous numbers of particles, and probability has a peculiar character. Given enough time, even extremely unlikely events can occur. A cup could, in principle, reassemble. Air could gather in a corner. Order could spontaneously return. But the timescales required are so vast that for all practical purposes, you will never witness such events. Not in your lifetime. Not in the lifetime of stars. The universe allows reversal. It simply buries it beneath overwhelming odds. This realization weakens another piece of your intuition. You thought time's direction came from necessity. You discover it comes from numbers. But probability alone does not fully explain why the world moves toward disorder so reliably, or why this statistical drift has such profound consequences for memory, causation, and the structure of experience. To understand that, you must confront a deeper concept, not force, not motion, but counting. You must confront what physicists call entropy. You think disorder is a kind of decay. You imagine a force that drives things to fall apart, a tendency toward messiness built into the world, a slow erosion of structure, a universal wearing down. But disorder is not a force, it is a number. To see this, return to the broken cup. Before the fall, the atoms of the cup occupy a very special arrangement. They form smooth surfaces, rigid structure, precise geometry. The number of microscopic ways to realize this exact shape is extremely small. After the fall, the fragments lie scattered across the floor. Now the atoms can be arranged in vastly more ways. The pieces could shift slightly. They could rotate. Tiny variations multiply the possibilities. The broken state is not preferred because the universe likes destruction. It is preferred because it can happen in more ways. This idea was made precise by Ludwig Boltzmann, who realized that what we call disorder is simply the number of possible microscopic arrangements consistent with what we see. More arrangements means higher probability. Higher probability means greater stability. This quantity, the count of possible configurations, is what physicists call entropy. Entropy is not chaos itself. It is the measure of how many ways chaos can exist. This is a subtle but devastating shift in perspective. When the cup shatters, entropy increases because the number of possible atomic arrangements increases. The system moves from a rare configuration to a common one, not because it must, because it almost always will. But something even stranger happens during this process. Information disappears. When the cup is intact, the positions of its atoms are tightly constrained. If you know the shape of the cup, you know a great deal about where its particles are located. After it shatters, that information spreads outward. Vibrations travel through the floor. Heat dissipates into the air. Tiny motions propagate into the surrounding environment. The precise details of the original structure become smeared across countless particles. The information is not destroyed. Physics forbids that in many situations, but it becomes hopelessly dispersed. To reverse the process, you would need to gather every fragment of this information. You would need to track every scattered vibration, every displaced air molecule, every microscopic change in the environment. You would need to reconstruct an unimaginably precise state of the world. The difficulty is not just rebuilding the cup. It is reversing the entire web of interactions that followed its fall. Entropy, then, is not merely about broken objects. It is about the spreading of information. And this spreading has a direction. Information disperses easily. It does not spontaneously reconcentrate. Heat flows from hot coffee into the cooler air. Sound waves radiate outward, not inward. Footprints form in sand, but do not unform themselves. These processes share a common feature. Information about the past leaks into the environment, becoming increasingly difficult to retrieve. This is what gives time its arrow, not a force, not a command. A one-way flow of accessible information. You experience the past as fixed because its traces exist everywhere, in memories, records, physical marks, radiation spreading through space. The future, by contrast, has left no such traces. The distinction between past and future emerges from this asymmetry. One direction contains records, the other does not. And suddenly the broken cup is no longer just an example of probability. It is part of a universal tendency for information to spread and possibilities to multiply. But this raises a more unsettling question. If time's direction comes from the way information spreads, why do you experience that direction so intimately? Why do you remember the past but not the future? Why does your own mind seem aligned with entropy's increase? To understand the arrow of time fully, you must now turn inward, toward the observer who watches the cup fall. You think time flows outside you. You imagine a cosmic clock pushing the universe forward, carrying you from past to future like a passenger. You assume your experience of time reflects something happening out there, but your sense of time's direction is not imposed on you. It is constructed within you. Consider what it means to remember. A memory is a physical record, a change in the structure of your brain. When you recall the falling cup, patterns of neurons have been altered by the event. The world has left an imprint inside you. Memory is not abstract. It is matter rearranged. And here is the crucial detail. The formation of memories always increases entropy. To store information, your brain consumes energy. It releases heat. It triggers chemical reactions. Order inside your neural structure is created by generating even greater disorder in the surrounding environment. Recording the past is a physical process that pushes the universe toward higher entropy. This is not optional, it is unavoidable. Your memories exist because the world moves from less probable states to more probable ones. They are traces left by entropy's increase. This reveals something disturbing. You remember the past not because the past is special, but because physical processes create records in one direction only. A shattered cup leaves fragments. A footprint leaves an impression. Light reflects from events and travels outward. Each of these produces a record of what has already happened. They embed information into the environment. But you never find records of the future. You never discover tomorrow's newspaper today. You never remember conversations that have not occurred. You never observe effects whose causes lie ahead. This is not because the future is fundamentally forbidden from influencing the present. The underlying laws of physics, as we saw, do not strictly prohibit such symmetry. It is because the creation of records requires entropy to increase, and entropy increases in only one direction. Your psychological sense of time follows this physical asymmetry. You remember yesterday because information about yesterday exists in accessible form, in your brain, in photographs, in scattered radiation traveling through space. The future has produced no such traces, so your experience of time's flow is tied to the direction in which records accumulate. You are not observing time's arrow, you are participating in it. Your mind itself is a machine that distinguishes past from future by generating irreversible changes. Every thought, every perception, every memory aligns your experience with increasing entropy. This transforms your understanding of what the past means. The past is not a region of time you can travel back to. It is the collection of states that have left traces. The future is not a destination awaiting arrival. It is the absence of records. Your entire experience of reality is organized around this asymmetry. And now the broken cup reveals something deeper still. To reverse time for the cup, to make it unshatter, would not simply require rearranging the fragments. It would require erasing every record of its breaking, every memory, every vibration, every trace in the environment. You would need to undo not only the event, but the knowledge of the event. You would need to reverse the physical changes inside every observer, including yourself. The implications are severe. If time's direction is defined by the creation of records, then reversing time means eliminating all records simultaneously. A universe running backward would contain no memory of its past, because what you call the past would lie ahead. The very concept of going back becomes unstable, and this leads to the next fracture in your intuition. If reversing a simple event demands reversing every trace of it, what would it take to reverse time itself? You imagine time travel as a local act. A machine activates, a person disappears. History rewinds for them alone. The rest of the universe continues, untouched. This picture feels natural. It is also wrong, because nothing in the universe happens in isolation. Return to the broken cup. When it strikes the floor, the event does not remain confined to ceramic fragments. The impact sends vibrations through the table. Sound waves move through the air. Heat spreads into the room. Light reflects from the shattering pieces and races outward at the speed of light. The event radiates consequences in every direction. Information about the cup's destruction leaks into the environment, into nearby molecules, distant walls, and eventually into space itself. A tiny flash of scattered radiation carries news of the event outward forever. The universe remembers. To reverse the shattering, you would need to reverse all of these effects. Not just the visible fragments, everything. Every air molecule disturbed by the impact would need to retrace its path. Every sound wave would need to contract back into silence. Every scattered photon would need to reverse direction and return to its source. You would need to recall the information that has already escaped. And here is the crucial problem. That information does not stay nearby. It disperses into an ever-growing region of the universe. Within seconds, the consequences of the event extend far beyond your reach. Within minutes, they have traveled astronomical distances. Reversing the cup requires reversing an expanding portion of reality. This is what makes time reversal fundamentally different from simply repairing damage. You can glue fragments together. You can rebuild structure, but you cannot restore the exact microscopic state that existed before the fall without controlling every interaction that followed. True reversal demands perfect knowledge of the universe's state and absolute control over it, nothing less. This is why the idea of stepping backward in time, of revisiting a previous moment while leaving everything else intact, conflicts with the nature of physical processes. Time's arrow is not a local feature. It is a global condition. The increase of entropy happens through countless interactions, linking every system to its surroundings. Each event entangles itself with the rest of the universe through exchanges of energy and information. To reverse time for one object, you must reverse time for all objects connected to it, which is to say, everything. This insight was deeply emphasized in the physical reasoning associated with Richard Feynman. The laws allow microscopic reversibility, but achieving it requires specifying the exact state of every particle, a precision so extreme that any deviation restores the forward march toward disorder. Time reversal is not forbidden. It is overwhelmingly unstable. The slightest error, a single misplaced molecule, a single stray vibration, destroys the reversal and returns the system to increasing entropy. The universe rapidly forgets the delicate conditions required for backward evolution. So the idea of a time machine faces a deeper obstacle than paradoxes about changing the past. The obstacle is statistical reality. You cannot reverse a moment without reversing the entire network of consequences that moment produced. You cannot isolate yourself from entropy's direction because your existence depends on the same irreversible processes. The universe does not block time travel with a rule. It dissolves it with complexity. And yet one question remains. If the laws of physics allow both directions, and if probability drives everything toward higher entropy, why did the universe ever begin in a state ordered enough for time to have a direction at all? Why was there a pristine cup to break in the first place? To answer this, you must confront the most unsettling idea of all. The arrow of time may not come from the laws of physics, but from the beginning of the universe itself. You imagine the universe began in chaos, an explosion, violence, disorder from the very start. It seems obvious. The early universe appears extreme, dense, hot, turbulent beyond imagination. Surely that must have been the height of disorder. But this intuition is backwards. The early universe was astonishingly ordered, not because it looked simple, but because its structure was extraordinarily specific. Matter was distributed with remarkable uniformity. Energy was arranged in a highly constrained state. The number of possible configurations matching this condition was extremely small. By the standards of entropy, the beginning was not chaotic. It was precise. This is one of the deepest mysteries in physics. Why did the universe start in such a special condition, a state so ordered that entropy could increase for billions of years afterward? Why was the cosmic coffee cup once so perfectly assembled? Because without that initial order, nothing you recognize as time would exist. If the universe had begun in maximum disorder, there would be no direction for entropy to increase. No arrow of time, no irreversible processes, no memories, no records, no distinction between past and future. Reality would simply fluctuate without history. The flow of time you experience depends entirely on this ancient asymmetry, a boundary condition set at the beginning of the cosmos. The laws of physics may be symmetric, but the universe itself is not. It began in a state that allowed disorder to grow, information to spread, and records to accumulate. The arrow of time is the long unfolding of that initial condition. Every broken cup is an echo of the universe's beginning. Every memory, every irreversible process, every trace of history reflects a single fact. The past was more ordered than the future. And here the story reaches its most unsettling point. We do not know why the universe began this way. Physics describes the increase of entropy with extraordinary precision, yet it does not explain why the initial state possessed such low entropy. The origin of time's direction, the reason the cosmic cup began intact, remains unresolved. The foundation of temporal experience rests on a mystery. This leaves you in a strange position. Time's arrow feels fundamental, yet it emerges from probability. Probability arises from entropy. Entropy increases because of the universe's initial condition. And that condition has no known explanation. The direction of time is not enforced by law. It is inherited from the past. You exist downstream of a boundary written into the structure of the cosmos, a condition that allows order to dissolve, information to disperse, and history to accumulate. And within this picture, time travel in the familiar sense begins to lose meaning. To return to the past would require reconstructing a universe of lower entropy, a state with fewer possibilities, fewer records, fewer traces. It would mean reversing the entire cosmic drift toward disorder, restoring a level of precision that existed only at the beginning, not forbidden, but unimaginably remote. The broken coffee cup on the floor is not merely debris. It is a small expression of a universal tendency stretching back to the origin of everything, the steady unfolding of possibilities from an improbable beginning. Time does not flow because reality demands it. It flows because the universe started in a condition that allows it, and the deeper you follow this idea, the more unsettling the conclusion becomes. The past is not simply behind you. It is the fragile order from which everything emerges. The future is not ahead. It is the vast sea of possibilities into which that order dissolves. You live at the boundary where structure becomes probability, where the universe continually forgets its own precision. And the broken cup, lying silently on the floor, is not proof that time moves forward. It is proof that the universe once began in a state delicate enough that it could fall apart.